Welcome to the Chapter 8 R Lab Part 2. In this lab, we're going to build a random forest and do some prediction on the Boston dataset. And this is the file for the Chapter 8 lab. I'm going to load some of the libraries that were used above. And what we're going to do, we're going to do predicting regression on random forest. So it's this part that we really care about in the code, but for comparison, and because we need the training and test split that's created for the Boston data, we're going to use this section here for fitting regression trees. So we're going to fit a single regression tree, compute the error for comparison, and then we're going to go on and build a random forest. And so in this part, we'll set up our training and test data for evaluation, and we will compute the regression accuracy for a single tree. So we'll need the mass library. The mass library contains the Boston data set. We need to set our seed so that we get the same results every time. And so we've created our tree. I'm going to walk through this quickly because we really care about getting to the random forest portion. We can plot our tree with our labels on our regression tree. We can plot the error, the deviance here as a function of size to do some pruning. So there we have our pruned tree, and we can do a prediction, and then we can set up a plot that helps us view our prediction and our regression, and so that's our result. 35.28 is our mean squared error. Now, I want to also have, for comparison, a linear model. So let's take some of these commands to set up that we use to set up our tree. And we're going to do this and create a linear model. So it's lm.tree. So this will create our linear model based on, we don't want lm.tree, we just want lm. This will create our linear model. Now we want to use it to predict on our training data. So we're doing a prediction using lm.Boston, which is our linear model, and we'll call the output from that lm.y hat. And then to compute the mean squared error, we use this command that we did before, lm.y hat. And so we see here that a linear model is doing better than a single regression tree. Okay, let's try a random forest and see how good that does, how well that does, and see how to build one and optimize it a little bit in R. So we need the random forest library. This is it's a good library for building random forest. We're going to set our seed, and then we're going to create a random forest. It's going to be called bag.Boston. Bag because remember, random forest uses two methods to create variation or decorrelate its trees. One is bagging, where you pull random samples of your data for each tree that you're going to build, and the other thing is when you create the split in each tree, you take some subset of the number of parameters, number of variables that are available. So this command will create a random forest. We're going to predict medium value as a function of everything from the data equals Boston data set subset, doing on the training subset. mtry is the number of feature variables we're going to try for each node, and then importance equals true tells this that we're going to keep the variable importance information. So this creates our random forest, and then bag.Boston, and we can see the input that went into our call. So we have a regression forest, 500 trees, 13 variables allowed at each split, and then here's some measures of accuracy. And so We can use this and predict on our training data. We can plot the predictions as a function of Boston test. And then we can look at the mean squared error. And the mean squared error here is 23.5. So to evaluate, compare, we had 35.28 for a single tree, 26.86 for a linear model, and now 23.59. We've gotten better using a random forest. Now we're going to build a second random forest. We're still going to have 13 variables, and we're going to only have 25 trees now. So let's build this new random forest. We'll do the predict, and I'll put that in y hat. And now our error is 23.6. So we see maybe going out to 500 is more than necessary because we get nearly as good results with 25 trees. And so at that point, there would be a trade-off. If you needed this predictor to run very fast, you might only use 25 trees. It didn't take very long to do the prediction with 500 trees, and I would just as well use that and be happy with a slight increase in accuracy, unless I needed sort of very fast performance. Now we're going to set our seed to be 1 again, and we're going to build one more random forest. This one, we're going to have 6 variables available at each node when we build the forest. And so we do our prediction, and we look at our mean accuracy, and our mean accuracy is 19.62, better still. So this 6, when mtry is 6, we get better results. We can look at the output for this. This has 500 trees, which is the default. If you don't specify how many trees, you're going to have 500 trees, and 6 variables available at each split. And now we can look at the importance of the variables. And remember, this importance you can measure in terms of an increase in mean squared error at each node that's used that variable, or an increase in node purity in the split when you use each of those variables. So we can also plot that variable importance. On the left-hand side, we have the percent increase in mean squared error. And so RM, and then LSTAT, and then CRIM, those gave us the best improvement in predictions when splits were made using those variables. And RM and LSTAT and CRIM, here really looking at node purity, RM and LSTAT were the leaders. Everything else seems to be lower down. If we want to know what, for example, RM and LSTAT are, we can take a look at our Boston data. And we have 506 rows, 14 columns of 14 predictor variables. And we have a prediction of the crime. It's MEDV, which is the median value of an owner-occupied home in thousands in that neighborhood. And the most important variables were RM and LSTAT. And so we can check what those are. RM is the average number of rooms in the home per dwelling, and that makes sense. And then LSTAT, lower status of the population in percent. So that has to do with socioeconomic status. And one more observation here, the total number of variables is 14. So there's 14 columns, or there's 13 predictor variables and one Y variable, one output variable we're trying to predict. So if you look back, these trees that we made originally, mtry equals 13, that was only using bagging because we set the number of trees in each of our random forests to be the full number sorry, the number of variables allowed at each node to be the full variables. So these first two trees we made were only doing bagging because mtry was 13. And then when we used mtry equals 6, that's half of the total variables. That's a good place to start for regression trees. Then we got a significant increase. And so we saw a nice increase using random forest over just ordinary bagging trees. If we wanted to optimize further, we would create some plots of accuracy as a function of the number of trees to pick our number of trees. We'd also look at some different values for mtry and see if we could improve things with that 6, because using half of your feature variables is a good start, but it's not guaranteed to be the best, and different data will require a different number for optimal performance. Thank you very much for watching.